Hello students, I thought of recording this lecture since I couldn't come to the class today. Okay, so let's see what we have discussed the last time. So if we have a population of interest and if we know it's normally distributed, okay, let's say, let x be the random variable of a population of interest Now, in the last time, from theorem 4, we learned that if x is normally distributed with mean mu and variance sigma squared, then let's say we are taking x1, x2 to xn be a random sample from the population then the sample mean x bar, which is the average of the samples, is also normally distributed for mean mu and the variance sigma squared divided by n. Okay, that was the theorem 4. That is when our population is normally distributed. And then the second case, the central limit theorem says, we learn about the central limit theorem when x is not normal, or it's not coming from a normal distribution, but the sample size n is large enough, then it does have two outcomes. One is the sample mean x bar is normally distributed with mean mu sigma squared on n as the variance, and second is n, which is simply the sum of xi's, is also normally distributed with mean n times mu and the variance n times sigma squared. This is only true when n is large enough, usually n larger than 30. And we went through, this is very important. These four theorems, theorem 4, 5, 6, are very, very important. You need to know them. You need to know how to apply them. The last time we did go through 2 examples, and today we're going to look a bit more examples. Okay. So they're very, very important, and you need to know them, and you need to know how to use them. We looked at this one last time, the example 5.4. Today let's go through the 5.5. The average demand for rental skis on winter Saturdays at a particular area is 120 pairs. There is a variation due to weather conditions and competing areas. The standard deviation is 20. We know the mean and the variance, or the standard deviation. The demand distribution seems to be roughly normal. Okay, roughly normal. The rental shop stocks 150 pairs of skis. What is the probability that demand will exceed the supply on any one winter Saturday? Okay, if we just consider one winter Saturday, first of all, we need to define our random variable. It's very important, very, very important to define our random variable because we're going to use a mathematical formulation of this question and answer it through scientific calculations. So the very first step is to define the random variable. let X be the demand for ski on a winter Saturday. If X is the demand, then we know it's normally distributed with mean 120 and the variance 20 squared. So we can use those facts to calculate the probability of X being larger than 150. So by normalizing it, subtracting mu and dividing by the sigma, we get P of Z larger than 1.5. This probability we can calculate as 1 minus P of C less than 1.5. Why? Because let's say this is the 1.5 and we want this probability, and that probability, so this is the P of C being larger than 1.5, and that probability is equal to the total probability, which is 1 minus this this probability, which is the cumulative densities of P being less than or equal to 1.5. And this one we can get from the table, the C table, or 1 minus P of 1.5 from the table value, and simplifying we get this number. For part 2, the manager will change the number of ski stocks for the next year. If the average demand is over 16 winter Saturdays, it's going to take statistics over 16 winter Saturdays. And if the average is over 125 or under 110, he's going to do some changes to ski stock. So if the population mean actually stays 120, so he's doing it by thinking that the population mean has changed from 120. But if we assume that the actual mean stay at 120, what is the probability that the manager will mistakenly change the stock? Okay. To answer that one, we are going to calculate a probability of mean being larger than 120 and being less than 120. So again, we need to define another random variable. Let X bar, this is very important, defining it is important, be the average demand over 16 Saturdays. If it's the average demand, then we can say that since the original population is normally distributed, from the theorem 4, we can say that X bar is also normally distributed with mean mu, which is 120, and the variance sigma squared divided by n. Sigma squared is 20 squared, n is 16. I wrote it as square root of 16 squared. Okay, which gives us a variance of 5 squared. So the required probability is the probability of mistakenly change the stock. That's happened when the probability of X bar being larger than 125 or X bar being less than 125, 110. We need to calculate these individual probabilities and add them together. How do we do that? Okay, to calculate X bar being larger than 120, we can use the fact that X bar is normally distributed and then standardize it by subtracting mu and dividing by its standard error, sigma upon square root n, which we already calculated at 5, which gives us the probability of C being larger than 1, which is also 1 minus the probability of C being less than 1, or 1 minus phi of 1, which we can calculate from the tables, the standard normal cumulative distribution number. The next one is when X bar is less than 110. Again, we can normalize it by subtracting mean and dividing by the standard error, which is sigma upon square root n, which simplified P of Z less than minus 2, but our table only have positive values, and since the normal distribution is symmetric, this probability is exactly the same as the probability of C being larger than 2, which can be calculated as 1 minus the probability of C being less than 2, or 1 minus phi of 2. And then adding those two probabilities, we get our answer. That one question, and let's look at the next question. The sports journal, again it's in a winter, published an analysis of critical part failure of NASCAR races. The researchers found that the time t until the first critical part failure has a highly skewed distribution with mean 0.1 and variance 0.1. Now consider a random sample of N50 NASCAR races. Let T bar represent the sample mean time until the first critical part failure. So now we're interested about the T time until the first critical part failure has occurred. And we have already defined the random variable T, and T bar is the average time, mean time until the first critical part failure. So the question asks us to calculate the expected value and the variance of this T bar. So in order to find out the expected value and variance of the T bar, we better first define T. Again, T denotes the time until the first critical part failure. This is very important to write. So the expected value mu 0.1, variance sigma squared is 0.1 squared. And we have a sample of 50. So now to answer the expected value of T bar, we know that it is same as the expected value of T, which is the mu, which is 0.1. And the variance of T bar, we learned that we learned that it is sigma squared on n. So plugging values, we get 0.002. Okay, now we know the expected value and variance of T, and then we can also get standard error of T bar is simply the square root of the variance of T bar. Okay. Now in the next part it asks, although T has slightly skewed distribution, the sampling distribution T bar is approximately normal. Why? Okay, because the central limit theorem says that when n is large enough, T bar follows normal distribution. That's the reason. And in our case, we have a sample of 50, which is good enough to apply the central limit theorem. So whenever we are going to apply a theorem, we always need to check whether the condition it has been met. So the condition for the central limit theorem to be true, we need sufficiently large sample size, and that has been met because 30 is usually considered as an enough sample size for skewed distributions. Okay, part C. Now we know the distribution of T bar, the variances, their expected values. So we can use those facts to answer the part C, which does ask find the probability that the sample mean time, which is T bar, until the first critical part failure exceed. So we want T bar exceed 0.13. So if I write it like this, that means the sample mean time exceed 0.13. And that's not what we want. What we want is the probability of that. So we need to write P of T bar less larger than 0.13. Okay, here we go. We want the probability of t being larger than 0.13. You need to write your answer similar to these answers written here. Have to write every single thing in the same order. Now, to calculate this probability, we can use the fact that t bar is normally distributed from the central limit theorem, and then we can standardize it by subtracting mu and dividing by its standard error, which is sigma point square root n, or subtracting 0.1 and dividing by the square root of 0.002. So that's the probability of z being larger than 2.12, and which we can write down as 1 minus the probability of c being less than. We always need to write it as a cumulative density function, the probability of c being less than some number, so that we can use the cumulative density function distribution tables for standard normal distribution. And from the table, we get this value. So the required probability is 0.017, which is about 1.7%. Very, very small. Very, very small. Okay, here we have more examples which you can go through at home. I have 1 and 2. Yeah, 2 examples. 2 more examples. So you can go through the solution and get a good understanding about this concept of the sample means. Very, very important. Now, the parameter estimation. Okay, suppose, guys, this is the second time I am recording this one, which is tiring. The first time, once I finish recording and check, there was no sound in it. The stupid computer. Oh my goodness, I had to do it again. Anyway, here we are. Now, we're in the chapter 6. It's about the parameter estimation. Let's look at the same example we looked at during the last lecture, which is the amount of sleep that young adult sleep. Okay, sleep of young adults. Okay, so let's say I'm interested about the average. Let's say I'm quite interested about the average amount of sleep. Why do I have a U here? I think you know U. Amount of sleep of young adults, because someone asked me to make the test easier. So this might be a useful quantity to make a decision about it. Average amount of sleep of young adults. Okay, we know that we have like millions of young adults in this world. So, and I don't actually know this. Let's call it as the mean. Let's say we use X. Let's say X represent the amount of sleep of young adults. So its average value, the expected value is mean, and we don't know this. What can we do about it? Rather just doing a random guess, we can take a sample. We can take a sample, and that means I select let's say 15 of you, and recorded how much sleep you had last night and take the average of it. Take a sample and get the sample average. Okay, and call X bar. Now I can say my X bar is an estimate for the mean. For the true average amount of sleep young adults get, I can have a point. This is actually a point estimate because it's just one value, point estimate. I can say, okay, I took an estimate of the sample average, and it is a point estimate. Point estimate means just one value, not an interval which having a range of value. X bar is just one value. That's why we call it as a point estimate. So in this chapter we're going to talk a bit more about such estimates. Okay. In this chapter we introduce the theory of point estimation, where unknown parameters, for example, the population mean, population variance, the proportions, success rate of a Bernoulli trial, are estimated by statistical computed from observed data. We observe data and calculate some statistic from them and estimate one of the parameters. Yeah, we want to estimate. We define point estimators and point estimators and point estimates, and we study how they. Okay, so the next thing we need to do is, once we come up with the point estimate, then we need to tell about how good they are or how bad they are, or some sort of accuracy of them. To talk about their accuracy, there are a few different terms or we can use. One is the biasness, variance, the precision, the standard error, or the mean square. So we're going to learn about them, which tells about how good these point estimates are. So knowing a good understanding about point estimate is quite useful to the fact that we're going to learn in the next chapters. In the next chapters, we're going to learn about interval estimates. For example, so mu is the one that is unknown, and as a point estimate, we took as X bar, and it's just one value. And if I use another sample, I might get a different value for the X bar. So it's not a very good way of just giving just one value as a point estimate. So there's a point estimate. It's the lowest best we can do. Rather giving just X bar, we can tell a range of value or interval of values that the mu can lie. Okay, so that would give a bit more information about mu. So that we're going to learn in the next chapter. And also we can perform some hypothesis testing to test whether the mean has been changed, mean has been increased, mean has been decreased, or we can compare two different means of two different populations, those sort of things that we're going to learn later on this course. So at the moment, let's focus a bit more about the point estimation. Okay, now let's suppose we have a sequence of data x1, x2 to xn collected as numbers collected through sampling from a distribution, from a population that depends on unknown parameter theta. So, for example, in this example of amount of sleep, we had no idea about the population mean or the mean amount of sleep of young adults. So, as a point estimator of theta, we calculate a statistic from the sample data. So, it is just some function of x1 to xn. So, x1 to xn are the data we collected. And we usually represent estimate with the hat. theta hat. So the observed value theta hat, this function quite depend on what is we are estimating, what parameter we are estimating. We'll come up with some examples, you will see it. And this observed value theta hat is called a point estimate. And it is the best guess of the value theta. Okay, let's look at some examples. Suppose we have collected x1, x2 to xn data coming from a population of uniform distribution. We know that it's between 0 and theta. Theta is the upper limit where it's equally likely to happen, which is unknown. Lower limit is 0, upper limit is theta, which is unknown. A common estimate for the upper limit is the maximum of the observed value. The maximum value. Maximum of the observed data points. And next one. Now let's say we have collected n data points from a population coming from normal distribution with known sigma and unknown mean. Unknown mean. So a natural estimate for the population mean mu is the sample mean. This is our sample mean. X bar. Okay, so now we know how to use sample data to calculate a statistic to estimate. So this is our point estimate mu hat for the mu. Okay, we know how to do it. Okay, now let's look at some properties of the point estimators. Let's look at how we can tell how good these estimates are through some quantities we calculated. One is the biasness. Nice. Okay, so we know that it's not good to be biased. As a teacher, I should not be biased to some students. I should be unbiased. Similarly, an estimate is also required to be unbiased. Okay, we prefer unbiased estimators. That's the preference. But how do we define it mathematically? If the expected value of our parameter, theta hat, equal to the parameter itself, then we call theta hat is an unbiased estimator for theta. All we need to do is we have to look at what is the expected value of our estimate theta hat. And if it's equal to theta itself, we call it as an unbiased estimator. And if it is not an unbiased estimator, the bias of estimator is defined as the difference of the expected value and expected value of the theta hat and the theta. Theta is the parameter we are estimating. Okay, now let's look at whether the sample mean is a biased estimator or an unbiased estimator. Okay, we have learned in so many places that the expected value of x bar is mu. So expected value of x bar is the expected value of mu hat, the point estimator, which means x bar is an unbiased estimator or estimator for the population mean mu. That meant good. X bar is a good one. It's unbiased. Here I have an illustration about being biased and unbiased. So let's say I have two point estimators, theta A hat and theta B hat for the population parameter theta. Now, if we look at the distribution of theta A hat, and its mean value has been equal to theta. You can see that the expected value of theta A had been equal to theta. However, in the case of theta B hat, when we look at its distribution, its mean value is not equal to the theta itself. So we have a biasness. So this distance is the bias of theta B hat. This is a bias estimate. So what we prefer is an unbiased estimator. Okay, here we have another example. It's about the binomial. It's about the proportion. Okay, estimate of a binomial proportion or the Bernoulli trial proportion. Consider a sequence of Bernoulli trials with a constant unknown success rate. Okay, we know that a Bernoulli trial, which give a success or failure, has a success probability, and somehow it is unknown. Let's say, for example, flipping a coin and looking at the probability of getting head. Usually, if it's an unbiased coin, the getting head should be 0.5. Success probability of getting head is 0.5. But now suppose we are in a gambling situation and someone has brought, we suspect that someone has brought an biased coin. Okay, and we don't know the success probability of getting head. For example, this unknown parameter can be estimated by conducting a sequence of trials and by observing how many of them resulted a success. So what we can do, we can flip that coin 100 times and check how many times it gives the head. So suppose that n trials are conducted and that the random variable x counts the number of successes observed. Then we know from the definition x is binomial. Binomial with the number of trials n and the success probability p. We know n, but we don't know p. Unknown. P is unknown. So, now a good estimate for p is defined as out of n, how many successes we got from the observed data. For example, 100 out of 100 trials, only 20 times got the head. So that's how we defined the proportion estimate. And now we want to know whether this is a good estimate or bad estimate. One way of telling its reliability is looking at whether it's a biased estimator or not. To tell about the biasness, we need to look at whether the expected value of p hat is equal to the p itself. Now, expected value of p hat is the expected value of should be x divided by n, not the p. And 1 on n can be pulled out from the expected value, as expected value is a linear operator, and we know for the binomial distribution the expected value is n times p. So we ended up with p. Good, very good. Since expected value of p hat equal to p, we can say p hat is an unbiased estimator of p. It's a good one. Here we have another one. Now, let's say we are drawing x1, x2, xn, and independent data from independent and identical distributed. Okay, let's say we are getting n independent samples from identically distributed random variable, and let's say that population we are drawing these data has a mean mu and the variance sigma squared, this mean unbounded. Sigma square less than infinity mean it's it's bounded. It's bounded. That means sigma squared is some value. It can't be infinity. Okay. Now, if we define sample mean like this, which is the sum of xi divided by n, this is, we can say this is a, we have already seen that since expected value of x bar is equal to mu itself, x bar, let me call it mu hat, is an unbiased estimate for me. We already know that. That's good. X bar is good. Next, we have defined the sample variance. The sample variance defined as 1 on n minus 1 sum of xi minus x bar squared. And we have to show that it is an unbiased estimate. Before that, let's look at how we define the population variance. This is the population variance. It's defined as 1 on n sum of xi minus mu squared, I 1 to n. Okay, let's compare them. In the sample variance, we subtract x bar. In the population variance, we subtract mu, because we know the mu in the case of finding variance. But since mu is unknown, we're going to use the sample mean instead. That's one difference. The other difference is here we divide on 1 on n, but in the case of sample variance, it's divided by n minus 1. Why? Why n minus 1? We're going to see that in a moment. Okay, so we have to show that s squared is an unbiased estimator for sigma. That means we have to show that the expected value of s squared equals to sigma squared. Let's do it. So here's the solution. So I'm going to start from here. We're going to rewrite this. X bar minus xi, I can write down xi minus x bar. I can write down as xi minus mu plus mu minus x bar. I add and subtract mu, which doesn't make any difference. Which I can say xi minus mu, and then from these two terms, pull a minus sign and write x bar first and then mu. Yeah, so that's what I have written here. Can write it that way. It doesn't change anything. And then let's look at, even before looking at the expected value of s bar, let's try to rewrite this summation in a different form, which is going to be useful. So if you look at the sum of xi minus x bar squared, for the xi minus x bar, I can write down like this. It's in the form of a minus b squared, where a is this and b is this, which we can write down as a squared minus 2ab plus b squared form. So this would be in the form of xi minus mu squared minus 2 times xi minus mu times the second term x bar minus mu. So that's the middle term, the last term is x bar minus mu squared. Okay, and so this square, this square we can write down as, we can expand with these three terms, and we can sum individual terms. Okay, so we have sum of the first term, the sum of the second term. In the second term, look, x bar minus mu, x bar is a value, mu is also a value, doesn't depend on n, I. So we can pull x bar minus mu out from the summation. And in the third term, this is again just a number. So we are summing this number for n times, which gives us n times x bar minus mu squared. Okay, now let's look at about this guy. Okay, so that guy, which I can write down as sum of xi minus sum of mu, I equal 1 to n, I equal 1 to n. So when we add xi for n times, it's same as n times x bar, because x bar is 1 on n, the sum. And when we add mu for n times, it becomes n times mu, which can be written as n times x bar minus mu, x bar minus mu. That's what's written here. So if we replace with that, the middle term simplified to 2 times n times x bar minus mu, one from here squared. And then these two are like terms, which simplified into n times x bar minus mu squared. Okay, next. Now we have sort of like simplified this sum. Okay, then let's look at its let's look at the expected value of this term. The expected value of this term is the expected value of the first term minus the expected value of the next term. So the expected value of the first term. So we know that expected value is a linear operator. So the expected value of a sum is the sum of the expected value. But from the definition, this term is the variance of x. That's the variance of x. That's how we define variance, which is sigma squared. So we are summing sigma squared for n times, which gives n sigma squared. So the next term, n times x bar minus mu. So expected value of n times x bar minus mu squared is same as the n times the expected value of x bar minus mu squared. And from the definition, this term is simply the variance of x bar. That's how we define the variance of x bar. And we know the variance of x bar is sigma squared on n, which simplifies to sigma squared. So, if we compute the expected value of this term, which is this term minus this term, which is n minus 1 sigma squared. But that's not what we really need. What we really need is the expected value of s squared, which is the expected value of this is the definition. And since expected value is a linear operator, we can pull out this constant term and say that is equal to the expected value of the sum of xi minus x bar squared. And earlier we learned that this term is n minus 1 times sigma squared. So it's n minus 1 and n minus 1 in the denominator cancel out and gives us a sigma squared. Okay, so you can see now why we had n minus 1 instead of n there in the definition of sample variance. So it's very important to know this definition. This definition, we define it this way so that s squared is an unbiased estimator. It's an unbiased. Because we always prefer unbiasedness. Okay. We have a few more minutes. Okay, let me just introduce the variance of a point estimator. Yeah, we already learned about this. The variance of the sample mean. we learned that it's sigma squared on n. Okay, so just a repetition. So the variance of a general estimate, this is for the sample mean as estimated for the mean. And how we define the variance of any estimated theta hat is simply from the definition of any variance as the theta hat minus the expected value of theta hat squared. So unbiasedness tells whether this point estimator accurately capture the center location of the distribution. That's one property. And the other property of an estimator is having a good precision. We define precision. The precision tells us about the variability of the estimator. So, if the estimator has a large variability, then it's not a good estimator. Precision of estimator refers how concentrated its sampling distribution is around its expected value. Precision is inversely related to the variance. Okay, so estimator with a smaller variance is more precise. I think, I'm not sure. If variance is small, precision will be large. Not sure. Need to check. I need to check this. Okay. So I need to check this. I'm not sure about this. But we prefer, what we prefer precise estimators. That means low variability in the estimate. Yeah, I'll stop here and we'll talk about this again tomorrow.